everyone, this is episode 007 of Real Physics, but we didn't get any James Bond material ready for this episode.
So instead, it's Dark Knight time! Let's flip a frickin' truck over!
For those of you not familiar with this movie, it's about a rich guy named Bruce who likes to cosplay as a bat.
And when he dresses up in his costume, somehow bad things happen and he gets in a lot of fights. Sometimes even with other cosplayers.
So in this scene, there's another cosplayer named Joker driving an 18-wheeler down a street when the man dressed as a bat hooks the front of the 18-wheeler with some fancy cables and secures the other end by weaving in and out of some street posts.
Now at this point, the truck reaches the end of the taut cables and over it goes in a perfectly straight line.
Damn those cables, I swear it's like Hoth all over again.
Now it's fairly well known this practical stunt was created with a real truck and a large piston in the back to help flip it over.
True, but ignoring that, what we're going to look at is whether or not an 18-wheeler has enough kinetic energy in it to actually stand itself up on its nose.
Right, and as usual, we're going to give this scene some best case credit, so when we're making assumptions or making estimates, we're going to err on the side of the scene.
So first off, we're going to allow the trailer to be empty. This moves the center of gravity of the truck forward.
And we will be ignoring the dubious amount of friction that a few hasty passes through some posts is going to provide, and treat the cables as rigid, also known as non-elastic.
We're also going to assume that the bumper of the truck, the street posts, and the cable could all handle this load. Also, it's a little strange that the trailer seems to be rigidly attached to the rig, but we're going to let that slide too.
What would really happen is the trailer would stay on the ground and the rig would flip up until it jammed the hitch, but we're going to let them get away with this since the center of gravity of the trailer might be directly behind the hitch pivot.
Okay, so the approach we're going to take here is to determine the kinetic energy of a typical 18-wheeler traveling at the speed that it appears to be going in this scene.
Then, by estimating the center of gravity, or the CG, of the truck and trailer, we can determine the amount of energy required to translate that CG to its upright position.
Right, but first, let's do some research.
Okay, real quick. Rigs are about 7,000 kilograms. An empty trailer this length is about 3,000 kilograms. A rig like this has a wheelbase of about 8.2 meters. This looks like a medium-sized trailer, so we're going to call it 12 meters.
Now the rig CG is going to be about 40% towards the front due to the engine, and the trailer CG is going to be closer to the back, probably around 60%. The trailer overlaps by about 2.5 meters, so we'll take that into account too.
So the total mass is 10,000 kilograms. Center of gravity is the sum of the positions times mass divided by the sum of the masses.
And using that, we find the position of the CG is 6.24 meters back.
Which is really not all that far back.
Not at all, but remember the rig is heavier, and its CG is in the front. Plus, this doesn't appear to be a full-on long trailer.
Now we need to find the vertical position of the center of gravity.
You know, data on this is pretty slim, but what we did find is NTHSA documents give a value called SSF, or Static Stability Factor.
The SSF is defined as 1/2 the track width divided by the height of the center of gravity.
It's used to compare the top heaviness of vehicles, and the SSF for an unladen rig is 0.8, and the track width is about 2.4 meters. Now a quick calculation, and we find that the CG of a typical unloaded rig and trailer is 1.5 meters.
Seems legit.
Okay, now remember, at the point that the truck is standing up on its nose, the longitudinal CG has now become its vertical CG. Also, the rotational energy at this point was 0, and as we move forward with the truck, it's also 0 at that point. So we don't have to consider that.
Okay, so it takes a lot of energy to take that center of gravity and move it from 1.5 meters up to 6.24 meters. So we're going to compare the kinetic energy of the rig traveling to the stored potential energy of that CG at 6.24 meters.
Right, now if the kinetic energy was still more than the stored potential energy when the rig was standing up, then we know there was enough energy to flip the truck.
Right, let's take a look.
Now from this scene, it appears that the Joker is traveling about really slow. We are going to make a guess though, and we're going to call it about 75 kilometers per hour or around 45 miles per hour.
Okay, so here's the equation for kinetic energy, and this comes out to be 2,170 kilojoules.
Now potential energy in a gravity field is just the mass times the acceleration of gravity times the change in height. Our change in height is the difference between the longitudinal CG and the vertical CG.
And that comes out to 463 kilojoules.
Wow, okay, that is 4 times the necessary kinetic energy required to flip the truck.
Okay, right, but realistically, some of that energy would be absorbed by the cables, which would act as a spring, and some of it would be absorbed by the elasticity of the bumper or converted into heat and sound.
You know what, though? Batman is obviously using advanced technology.
Yeah, so advanced, it's indistinguishable from magic, and, you know, we really can't comment on how strong or elastic his rope is. I don't know, maybe we're giving the scene too much credit.
Well, you say that, but if we trim back to only the energy required to flip the truck, it would still only need to be traveling 38 kilometers an hour or 23 miles per hour, which is really, really slow.
Okay, wait. In that scene, the truck was still rotating pretty well when it got up to the top, so some of that kinetic energy was still there.
That's true, but you know, after it was all said and done, there were so many variables involved in doing this stunt, it made it very difficult for us to try to analyze it.
And that's why we chose to focus just on the kinetic energy versus the potential energy of the rig.
All right, well, let's call it.
Okay, we're going to give this scene some credit, and we're going to call it real physics.
All right, there you have it. Until next week, thanks for watching.
Drive safe in your cosplay.
Hey, I know you're gonna do it.
I won't. I promise I won't do it.
Hey everyone!
I'm Colby! God damn it!
Hey everyone! God, I was sticking my tongue out when I started.
Okay, so it's fairly well known that this practical stunt was created with a real trunk. I did it first. Okay.
So the approach we're God damn it! All right, so remember, gang. Gang, I don't know. Gang. Really. Stop it!
I didn't do anything!
Okay, here we go. Damn those cables! I swear it's like Hoth all over again.
Dude, that joke is cold.
You know that joke I just said? It took me a while to plan it.